You filthy swines! Get in here, sit down, behave yourselves. We're going to read some news. Another potential solution for the Fermi paradox is there are artifacts out there that are clear indications of intelligent design, but we are compulsively explaining them away as natural phenomena. So I find it very interesting when anomalies are discovered, and I like to contemplate what those anomalies might actually be. Potentially they are examples of super civilizations, or perhaps clues at a much deeper understanding of physics, maybe. I don't know. We'll find out more on this article from Science Focus, written by Dr. Becky Smethurst. I think I've watched Dr. Becky on YouTube. She's pretty awesome, actually. You should check her out. She does lots of cool physics stuff. The new mystery hidden inside the universe's biggest ever black hole. Black holes are big, very big, but physics makes it almost impossible for them to grow. Here's how one black hole defied the odds to swell to gargantuan proportions. Now, my take on this is perhaps this huge, humongous black hole is the remnant of some kind of alien conflict, a war. If you could create a bomb that turns a star into a black hole and you were in a dark forest scenario, perhaps you might like to turn the suns of a civilization into black holes. You could create a whole galaxy of black holes instead of suns that would then aggregate and create a gargantuan black hole. I don't know. This is my speculation. Now we're going to read it and I'll shut up. The first image taken of a black hole, the picture that finally turned artists' impressions into a reality, was of the supermassive black hole at the center of the galaxy, Messier 87. Most supermassive black holes are found in the centers of galaxies. They sit in the gravitational driving seat as hundreds of billions of stars in the surrounding systems happily orbit them, just like the planets orbit the Sun at the center of the solar system. The black hole at the center of Messier 87 lies at the more massive end of the supermassive scale, cramming a mass of 6 billion times that of the Sun, 6 billion solar masses, into an area the size of Neptune's orbit. Still pretty big. Neptune is, well, the last planet in the solar system, unless you're going to whine about Pluto and its wonky egg-shaped orbit. But as huge as that might sound, especially when compared to the black hole at the center of the Milky Way, which is a mere 4 million solar masses, it's tiny. It's by no means the most massive black hole that we know of. That title goes to Ton 618, which is an astonishing 66 billion solar masses. It's so big that astronomers had to invent a new term to describe it, hence Ton 618 is what became known as an ultra-massive black hole. To give you an idea of just how mind-bogglingly big Ton 618 is, imagine taking all the stars in the Milky Way and squishing the matter in them down to create a black hole. Even if you did that, you would still be a few billion suns worth of matter shy. So how did Ton 618 become such a behemoth? Interestingly, it is as massive as a galaxy larger than the Milky Way. So if there were a civilization that had managed to colonize the entire galaxy, and another civilization came along and said, "You suck, we're going to turn your suns off," would that be what happens? What would really happen if you got near a black hole? Black holes are made of vast amounts of matter that have accumulated in one spot and have been packed together as densely as possible to the point where the gravitational pull from the accumulation is so strong that not even light can escape it. But that doesn't mean that a black hole is a giant monster with an insatiable appetite, roaming the universe and devouring everything it encounters. Ton 618, the most massive black hole we know of, still has an entire galaxy of stars happily orbiting it and not getting sucked in. It's a common misconception that black holes act like vacuum cleaners, when in reality it's incredibly difficult to grow a black hole. There's not even a YouTube video to show you how to do it. For a start, you have to get material close enough for it to be affected by the black hole's gravity. And when you consider how dense black holes are, due to all the matter being squished into a tiny space and how vast the universe really is, you start to realize just how difficult that can be. If matter does stray too close, however, it will get pulled in by the black hole's gravity, and that gravity increases dramatically the closer you get. Think of it like walking up a hill, but the hill becomes steeper with every step you take. It's brutal. The gravity around a black hole increases so quickly that if you were to approach one with your feet first, the pull of gravity at your feet would be so much stronger than at your head that you'd get stretched out like spaghetti. In perhaps the best example of jargon the science world has to offer, the process is legitimately referred to as spaghettification. Would that not just tear you apart? Instead of a stretchy Armstrong man, would that not just be a streak of red? We see this happening to stars and clouds of gas as they get closer to a black hole. Once spaghettified, the matter then gets pulled into orbit around the black hole and flattened into a swirling disk of material. The process is similar to the way you create a pizza base by tossing the dough above your head. As it spins, the dough gradually flattens out. Once it's in that spinning disk, the matter, usually hydrogen gas, as this is the most common element in the universe, will settle into a nice, happy orbit around the black hole, far away from the point of no return, the event horizon. The event horizon is the sphere around the black hole that we use to ascertain its size. The larger the event horizon, the more massive the black hole. While the matter inside the event horizon is being crushed down to an infinitesimally small scale, known as the singularity, the size of a black hole is taken to be the region of space from which we no longer receive any light. It's the distance away from the singularity where you'd be traveling faster than the speed of light to escape the black hole's gravity. If you cross the event horizon, you're done for, officially part of the black hole and contributing to its total mass forevermore. But getting matter to cross the event horizon is what's so difficult about growing black holes. How do you move material out of a happy, stable orbit around the black hole and get it to fall in, helping the black hole swell to massive proportions? The Sun and Earth provide a good demonstration of the difficulty. Earth is in a stable orbit around the Sun, and despite the star's huge size and far greater gravity compared to our planet, it's thankfully unable to pull us in towards it. What actually falls into a black hole? The reason material is able to cross the event horizon is collisions between particles in the disk of material orbiting it. Atoms of hydrogen gas collide and transfer energy, just like balls on a snooker table or a pool table. If you're a talented pool player, you might be able to hit the cue ball against a colored ball and get the cue ball to stop dead, transferring all of its energy to the colored ball, which shoots off across the table. A similar exchange in energy can happen to colliding particles in the disk of material orbiting a black hole. The particle that gains all the energy will get a boost, pushing it further away from the black hole. But the particle that loses its energy will have nothing to resist the gravity pulling on it, and gradually slide down to cross the event horizon and become part of the black hole. Not every collision will result in such a drastic energy exchange. On average, there will be an equaling out of energy. But eventually, one particle will have enough collisions and be unlucky enough to lose energy in every one, bringing it ever closer to the black hole. It's only when the particle has a collision in the region known as the innermost stable circular orbit, ISCO, that it will finally cross the event horizon to become part of the black hole. The ISCO doesn't exist in Newton's theory of gravity, which we all learn at school. Newton's theory says that all perfectly circular orbits, no matter their distance, are very stable. That means if an object on a circular orbit is unsettled slightly, it'll remain largely on the same orbital path. For instance, if something was somehow orbiting the Sun in a near-perfect circle and was nudged by another object, its orbit might become more oval, but it would continue orbiting the Sun. That's not the case in Einstein's theory of relativity, however. As you get closer to an object like a black hole, there comes a point where if you nudge an object on a circular orbit, or say one particle were to collide with another, that object couldn't correct its path and would end up spiraling in towards the black hole. That point is the ISCO. It lies around 3 times further out than the event horizon and usually marks the inner edge of the orbiting disk of matter. This process of particles colliding, exchanging energy, and falling over the event horizon at creation takes a very long time. We're talking millions of years just to get a black hole to a size where it can snack on a passing gas cloud that drifts too close. How much matter can fall into a black hole? Well, I imagine an unlimited amount, but what do I know? Complicating matters even further is the fact that there's also a limit to how much matter a black hole can accrete in a given time. The universe effectively puts a black hole on a diet if it becomes too gluttonous. This happens because the disk of matter orbiting a black hole is moving and colliding at such an incredible speed that it starts to heat up due to friction. It's heated to such an extreme temperature that it glows like metal a forge. The good news about this glow is that it allows us to spot black holes and measure how massive they are. The light can and does outshine entire galaxies, making them look like single pinpricks of light. These pinpricks were originally dubbed quasars, a portmanteau of quasi-stellar because they look like stars but they aren't stars. It was only after Hubble's Space Telescope launched in the early 1990s that astronomers could make out the galaxy of stars that went with each quasar, and their true role in growing supermassive black holes was revealed. The bad news for black holes is that the glow is so intense that it exerts a pressure outwards. Radiation pressure that prevents any more matter from falling in. There's too much material in the disk, the radiation pressure increases and pushes material away from the black hole. There's a fine balance between the size of the black hole and the quantity of matter in its disk, and when a certain threshold is reached, depending on how massive the black hole is, the rate at which it can accrete material is capped. How big can black holes get? Pretty ruddy big, I imagine. What makes Ton 618 so exceptional is the sheer amount of physics standing in the way of a black hole growing to that size. But while we know for a long time that radiation pressure places a limit on how fast a black hole can grow, known as the Eddington limit, after astronomer Sir Arthur Eddington, who sounds like a good chap, what we didn't know until recently was whether there's a limit to how massive a black hole can become. As far as we know, there isn't. Theoretically, you could keep on merging black holes to your heart's content, gradually increasing the overall size as if you were making a giant snowball. But there is a limit to how big black holes can grow via accretion. In 2015, Professor Andrew King of the University of Leicester published a paper that pointed out a quirk of gravity around black holes. The quirk allowed him to estimate the maximum mass a black hole could achieve via accretion, 50 billion solar masses, but it could be 270 billion solar masses if the black hole was spinning fast in the same direction as its galaxy. There we go, there's a size comparison there. At the root of this quirk is the position of the ISCO, which, like the event horizon, is related to how massive the black hole is. As the black hole's mass increases, the ISCO gets pushed further out. The problem for growing a black hole is when the ISCO is pushed beyond what's known as the self-gravitational radius. The distance that the self-gravitational radius sits around a black hole is another factor that is related to the mass of the black hole, but it also depends on the object that's approaching it. The self-gravitational radius marks the point at which the pull of gravity holding the approaching object, self-gravity, is stronger than the pull from the black hole. The self-gravitational radius is why we're all here. It's why we're all able to have entire galaxies surrounding supermassive black holes. Beyond this radius, gas in a galaxy is attracted more to itself than to the black hole lying at its center. If this wasn't the case, gas would never collapse to form stars, and instead our atoms would just be part of one giant disk of material orbiting a supermassive black hole. It was King who pointed out that when a black hole reaches 50 billion solar masses, the ISCO gets pushed beyond the self-gravitational radius. What that means is that no matter how many collisions they have, any particles in the disk of material orbiting the black hole will never lose enough energy to reduce their orbits to a point that allows them to reach the ISCO and spiral into the black hole. Instead, the pull of gravity from all the other particles in the disk will always be stronger than the pull from the black hole. That's if there is a disk of material around the black hole, because any matter that isn't on a direct bullseye trajectory with the singularity as it approaches won't get pulled into the disk. Instead, it will loop around the black hole, spaghettified but otherwise unscathed. This lack of a disk means that we also won't be able to spot such a black hole, as there'll be no luminous matter around it lighting up like a Christmas tree. Although I imagine you'd get some clues from any lensing. Stuff behind it may seem bigger. This is why Ton 618 is so interesting to astronomers. With an ultramassive black hole of 66 billion solar masses, it lies above King's estimate of the maximum limit, 50 billion solar masses, for a non-spinning black hole. Most black holes are spinning, which increases the mass they can reach before they push the ISCO beyond the self-gravitational radius. But it still means that Ton 618 could be nearing its maximum possible mass, past their prime. It's fascinating to consider the implications of all this. We could be approaching the point in the universe's history in which black holes start reaching their limit. If black holes stop accreting and growing in this way, then they'll also stop glowing. quasars will begin to wink out as black holes age past their glory days. It's possible that there are other black holes in the universe that have already reached ultramassive proportions. You can try hunting for them, but without the glow of a disk orbiting around them, we'll never spot them. There could be ultramassive black holes hiding right under our noses. There could be. But there are lots of fantastical explanations that you could throw at this. Perhaps it is the result of a galactic war. Perhaps it is being created as a monument. If it's impossible for this thing to have accreted naturally, then maybe that's a good indication that it's not natural. But nothing in this article suggests that, because I think Dr. Becky is a legitimate scientist and I'm just a sci-fi nerd. I like this stuff, find it fascinating. But it's worth contemplating that this may, who knows, be something less natural. It's itself larger than the Milky Way, and yet it still has a galaxy orbiting around it. So what does that mean? What could that mean? Could it have been a collision between two galaxies, of which one had an established noisy species and the other had a stealthy dark forest type quiet species that then black holed all of the other galaxies' suns, maybe? That's an interesting storyline. We could go along with that. Perhaps it is a monument of sorts. Maybe it's been put there as a beacon to say, look, there's intelligence here. This is completely unnatural. Who knows? Is there any benefit in creating a black hole? Can you hide information? Can you process information in there? Is there some benefit in being inside of a black hole? Is that even possible? I don't know. I'm just asking questions. I'm just asking questions. That's what we do here. We just ask questions. Lots of potentials there. Good article there, Dr. Becky. I like you. I like you a long time. Go check her out on YouTube. But that is it for now. Make sure you hit that like button. Subscribe if you can. The best place to subscribe is x.com/ultraswinery. And the only thing I have left to say is Pigwig out.
Oink, oinkity, snort, snuffle, snuffle, squee, oink, oink, wee, squeal, snort, snort, oinkity, squee. Oink, 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 squee, squee, wee, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 wee, 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 oh. Snort, snuffle, oink, squee, squeal, wee, snort, oinky, oinkity, oink, oink, snuffle, wee, squee, snort, oink, squeal. Oink, 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 squee, squee, wee, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 wee, 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 oh. Oink, oinkity, snort, snuffle, snuffle, squee, oinkity, oink, oink, snuffle, wee, squee, snort, oink, squeal. Oink, 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 squee, squee, wee, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 wee, 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 oh. Squeal, squeal. Snort, snuffle, oink, re-squeal, re-snort, oinky, oinkity, oink, 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 snuffle, re-squeeze, snort, oink, squeal, oink, oink, oinkity, squee, squee, re, snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 re,